the charge is equal to coulombs, and then the voltage is in volts, so hey, this is equal to joules. The charge on an electron is equal to, okay, so charge of an electron is equal to 1.6 times 10 to the minus 19 coulombs. Anyway, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Okay, so let me write that down. So 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So how much energy is in 200 mega electron volts? Okay, so 200 mega electron volts. So this is, so again, it'd be nicer if everyone just used the same energy units, but then they don't. So in food they use calories, and in Britain they use BTUs, British thermal units, and I guess in nuclear physics and chemistry they use the electron volts. So anyway, how much is the prefix mega? Is how much? Mega is 10 to the 6. Yeah, 10 to the 6 or a million. Okay, so that's 200 million electron volts. So 200 MeV is equal to how many joules?
3.2 times 10 to the negative 11.
3.2 times 10 to the minus 11 joules. Okay, so what this means is that when one U-235 nucleus undergoes this nuclear reaction, this amount of energy is produced per nucleus. Okay, so I'm going to say 3.2 times 10 minus joules per U-235 nucleus. So based on this number and on the number 8.36 times 10 to the 13 joules, how many U-235 nuclei do you need to produce that same amount of energy? Okay, so what we're doing is we're saying that this is the amount produced per nucleus. That's the total amount of energy, 8.36 times 10 to the 13 joules. So the number of U-235 nuclei that we need is equal to, okay, so we have 8 point, let's see here. Okay, so we know the energy per nucleus. If we multiply this by the number of nuclei, this is going to give us the total energy. Okay, so we know what the total energy is. This is 8.36 times 10 to the 13 joules. And we know the energy per nucleus, that's 3.2 times 10 to the minus 11. So let's solve for x, and that gives us the number of nuclei we need. So, George, you calculate x is equal to times 10 to the 24th nuclei. So this is going to be U-235 nuclei. So what is the mass of 2.6 times 10 to the 24th U-235 nuclei going to be? So let's convert this to mass. And how do we do that? Okay, so 235, this is this tells us this is the mass number or the atomic weight or molar mass. In other words, if you have 1 mole of U-235, that has a mass of 235 grams. So in other words, 235 grams per mole. So if we have the number of nuclei, then we can convert from nuclei to moles, and then from moles to grams. Let's do that. So we have this number. Okay, so we have let's write that here. So we have 2.6 times 10 to the 24th. This is U-235 nuclei. And let's see. We need to divide by Avogadro's number, 6.02 times 10 to the 23rd. Nuclei per mole. Then multiply this by 235 grams per mole. And that's equal to
114.115.
what's that again?
1014.9 to 1015.
1014.
It's actually 1015.
1015, okay, so this is going to be 1015 grams, or approximately 1 kilogram of U-235, assuming all the nuclei undergo this nuclear reaction, will produce the same amount of energy as 20 kilotons of TNT. And then I looked up the density of U-235, and let's see, the density is, let's see, the density is 19.1 grams per cubic centimeter. So that means that's a sphere of diameter 5 centimeters, or about 2 inches, which is, what is that, the size of between a golf ball and a baseball? So that's why all those fantastic, sensational movies are, involve these nuclear events happening, because you don't need much. You don't need much to cause a lot of mayhem, and that's what people like to see movies for. Mayhem, because you can't do that anymore. You know what it's called. Okay, so anyway, there's a lot of energy released in the atomic bomb. Now, let's go on to the next slide. Now, in a nuclear power plant, the uranium-235 was also used, but note that it only has to be enriched from 0.7% to 2 or 3%. So there's a big difference between the enriched uranium in a nuclear power plant compared to an atomic bomb. Okay, so again, the enriched uranium for a nuclear power plant is 2 or 3% from 0.7% versus 90% for a bomb. Okay, so when you hear these stories saying that, oh, the uranium from a nuclear power plant can be used in a nuclear weapon, well, that's wrong. Well,
they could be.
Well, they could be, but you need some really specialized equipment.
Or you could just get a bunch of nuclear waste and blow it up, and then it's a dirty bomb.
Yeah, that's true. Okay, so anyway, there's another chain reaction involved in a nuclear power plant. There are different types of reactors. Anyway, there's the fuel rods, control rods, moderator, the coolant. How does a plant work to produce electricity? Let's take a look at the next slide, because it shows, we found a diagram from how stuff works and how a plant works. So anyway, here is the nuclear reactor here. Okay, not too easy to see. So anyway, we'll go by letter. So A, this is the containment structure. That's usually made of thick concrete. B is the control rods. Now the control rods are usually made of something like boron or cadmium, and the control rods are inserted between the fuel rods. The fuel rods are made out of the uranium-235, and when the control rods are inserted between the fuel rods, what do you think those control rods are supposed to do?
Absorb
They're absorbing Not electrons, neutrons. Okay, so remember if we go back to this reaction, note that these neutrons collide with U-235 to make this reaction go. Okay, so if we can actually slow the rate of reaction, again, these are these reaction rates principles we talked about earlier. If we can decrease the amount of neutrons, that's going to decrease the reaction rate. Okay, so those control rods control the rate of reaction.
But they can't stop it, right? You can't stop it. But you can stop
No, you can't stop it. You can just slow it down. Okay, part C is the reactor. The fuel rods, okay, they're not really showing the fuel rods. Here's the reactor with the fuel rods. Part D is the steam generator, which is right over here. So note that the steam generator, so note that the heat produced from this nuclear reaction heats up this water, produces steam. Note that once the steam is produced, it goes through the steam line and it goes to H, which is the turbine. So note that the steam is turning this turbine. And then you know from physics 4B or 4C from electricity and magnetism that when you have what is it, this coil spinning around a magnet or something like that, that's how electricity is produced. Is that how it works? I can't remember Maxwell's laws from 1970 something like that. Physics 4 something, 4B or 4C. That was a long time ago.
When you have a meltdown, what is that? What will happen?
Now we'll talk about that. You're not answering my question. Okay, so anyway, since we're not talking about how electricity is produced from a magnet and a coil, we'll keep on going. So anyway, the turbine spins, that produces G, the generator, and then it goes off to our power lines to our homes. Okay, so anyway, they show K, here's the fuel rods, here's our cooling tower. What's the cooling tower used for anyway? Yeah, so note that once the steam passes through the turbine, it's got to be cooled. That is condensed back into water. Okay, so there's some heat exchange going here. That's what they're. What's the stuff coming out of the cooling tower? Is it radioactive here? No. Stuff here? That's supposed to be steam. So steam should be radioactive. Will not be radioactive. And then the water goes back through. Okay, this gets pumped back into the steam generator. Here's a coolant here. Anyway, this is how our nuclear power plant works. Let's go back one slide. So let's see. The function of the fuel rods is to do what?
Power.
Yeah, so this is going to produce heat. The control rod we just talked about. What's the moderator used for?
Temperature.
Yeah, so let's go back here. So the fuel rods are placed in water. And actually it's the water which is used to cool down the fuel rods. So actually, if the water wasn't there, because the water is actually used as not just a coolant, but also as a moderator. Okay, so it also moderates the the nuclear reaction as well. Okay, so water in this case is used as a moderator as well as the coolant. And then the coolant is also in this case the water. So Bruce asked the question about meltdown. So what happens when a meltdown occurs?
Circulation of water.
So note that the fuel rods are what state of matter?
Solid.
Yeah, solid. So a meltdown occurs when the fuel rods melt. Okay, they get too hot. Okay, so that's what happened in Japan when the tsunami hit. They couldn't pump enough water to cool down those fuel rods, and they started getting a meltdown. They started melting. Okay. What is one advantage of nuclear power? What is one disadvantage of nuclear power? So are any of you in the camp, they have this acronym, you've seen it before. Are you in this camp? NIMBY? NIMBY? Are you guys in that camp? What does that stand for?
Nuclear something.
Nuclear something.
No, it stands for, so this may apply to nuclear as well as others. Yeah, not in my backyard. If you want a power plant in your backyard? Yeah, so I was listening to a story on fracking, the fracturing of these rock formations to get natural gas. And a lot of these fracking wells are in Colorado and Utah, or they're in people's backyards. I guess the law is they have to be 150 feet or 50 yards away from a person's house. But I guess when you have this tall structure in your backyard, 150 feet away may seem a lot closer than that. Anyway, let's go on to this. Here's you want a nuclear power plant in your backyard, so in 3 Mile Island. Was any radiation released in 3 Mile Island? No. It turns out that in 3 Mile Island, the containment vessel did contain the radiation which was produced from that meltdown. Actually, a lot of these nuclear power plants, they have several containment vessels. So, for example, the reactor is placed on like a concrete liner, and then that's placed around like a steel containment vessel, and then that's contained around this very thick containment vessel here. Okay, so usually there's 3 containment vessels in a nuclear power plant. So it turns out that in 3 Mile Island, 1979, that third containment vessel was not breached, so no radiation was actually released in that 3 Mile Island accident. In Chernobyl, was any radiation released?
Just a little.